Hello, my name is Matt Ruffner, and I'm here presenting you the final project for EE699 IoT software hardware design taught by Dr. Takar at the University of Kentucky, spring 2019. My project is called MeasureMesh, and it is a long-range wireless measurement system and analytics interface. Let's get started. So wireless monitoring in general has a lot of applications. That's pretty valuable to be able to just see real-time statistics on a computer dashboard from sensors that are distributed with large spatial deviation. It has uses in agriculture, monitoring of crops, soil temperatures, water temperatures of the irrigation systems, biomedical uses such as implants, being able to communicate with implants, and also being able to monitor body temperatures of people is also useful. And then, of course, the ubiquitous household application for monitoring the temperature of different rooms. It can revolutionize climate control. It can also let you monitor your outdoor temperatures. So the LoRa standard, which I'll talk about a little more, is a ISM band radio protocol. ISM stands for Industry, Science, and Medicine, and it's the open RF frequency for these devices. It's around 900 megahertz, what your old typical cordless phones were before 2.4G got popular. And again, like I said, the ease of data visualization improves the system utilization, in that if it is easier for people to see the data they're monitoring, they're more likely going to use your system. So let's look at the LoRa overview here. This figure is taken from the LoRaWAN standard website. The link to this image is in my report. So key aspects of LoRa that are good. We got low power, it's encrypted, long range, and it's actually a variable bit rate standard. It depends on how well it is currently receiving. It will do an adaptive bit rate algorithm to make sure that the communication integrity is not sacrificed. So this figure here kind of gives you a overview of a system that would be implemented with a LoRa. So this kind of has a gateway, a node, and a server all in it. And this shows the end-to-end encryption you get with using the LoRa radio as a packet forwarding mechanism. It shows the IP stack and the physical layer of the LoRa radio. And the actual LoRa radio that I'm using in this project, you'll see in pictures here coming up quick, but it's RFM95. It's a Radio Fruit, and it's an implementation of this ISM band LoRa radio that you see in the middle of this figure here. So a quick overview of the MeasureMesh hardware that I've put together here. So your basic endpoint that senses the data is going to be a node, and that transmits via these LoRa radios to the gateway, and this gateway communicates over serial to the server. Now it can also communicate over Wi-Fi to the server, because I've chosen my gateway to have Wi-Fi capabilities. So you can either have a hard connection to the server, or it can be a Wi-Fi based connection. Now the server in this case is actually my home Linux machine at my house, and I have the gateway directly plugged into that. I would have liked to have done a Wi-Fi connection at school to be able to demonstrate it earlier than finals week. However, the processor does not support the WPA2 Enterprise that EDU Rome uses. So getting it online on campus is a hassle, unfortunately. So I decided to just go with a serial connection at home because the end result is basically the same. So this is an overview of the hardware. Now we'll go in and specifically look at the node and gateway hardware. So for the node, what I've done is I've used an off-the-shelf Atmel processor that is spun up on a custom circuit board by Adafruit with the radio module already on it. So it's very handy. It has built-in micro USB, built-in Molex connector for a battery, a built-in LiPo battery charger with current regulating capabilities and status indication LEDs. And I've also purchased a 900 megahertz half-wave whip antenna from Adafruit that plugs in to a micro UFL connector on the bottom of the board and then onto a SMA connector for the half-wave whip antenna. And it's pretty straightforward. I didn't even actually add any external circuitry. I just programmed this. It's Arduino compatible. It's pretty straightforward. It's really a great board. That board costs about $35 that has the radio on it. And then there's a LiPo battery sitting under there in the figure in the bottom right, as well as the antenna, and all that put together costs about $53. That's not including the cost of the material for the printed enclosure, but that's negligible compared to the rest of it. And you know, talking about the 3D printed enclosure, it's just a simple CAD design I threw together with some mounting holes based around the dimensions of the board that I bought from Adafruit, with a hole in one end for the antenna and a hole in the other end for the micro USB port. And there's a little lid. I didn't bother showing the CAD rendering of the lid because it's pretty obvious from the pictures, but it snaps on. You can see there's a little recess, and it generally looks nice. You know, it's attractive. So that's the node. Now gateway. So the gateway here is again the same LoRa radio. You can see that on the left of the breadboard. There's that green PCB mounted onto the blue PCB. The green PCB itself is the radio. There's some level shifting and voltage regulation going on the blue carrier board, and that's just a simple SPI interface to the breakout board of the ESP8266, which is another Wi-Fi enabled Arduino compatible processor that I can connect over USB serial to my server. And this is what entails the gateway. And there's some Arduino code. You know, the gateway firmware.ino in the repository is what's running on this chip, and it's pretty straightforward. I mean, the circuit's not complicated. It's a direct SPI connection. There's a reset pin. There's an onboard voltage regulator. There's an IRQ pin. You know, it has interrupt capability so that the microcontroller doesn't constantly have to poll to see if there's new radio packets. You know, this could be used for an interrupt-driven sleep routine, etc. So this is the design of the gateway. So the idea here is you would have one gateway for many nodes. Let's say, you know, up to however many of these radios support, which I think is 8-bit. So I'm pretty sure you could have 255 nodes for one gateway, which is pretty good. And this only costs 25 bucks. Most of that's the cost of the radio. I think 20 of that's the cost of the radio. These ESP8266s are super cheap. This is just an Amazon spin up, you know. Not super reliable. You can see that button's pretty crooked, but it definitely works. So moving on. This is an overview of the node firmware. You can see I have a flow chart describing its nominal operation. Basically, I describe the processor a little more in depth. You know, again, this Atmel processor has a rich peripheral set. You know, 48 megahertz SPI I2C, has DMA capabilities, has multiple timers and interrupt capabilities. So if you wanted to, you could really connect a pretty wide variety and number of sensors to this processor for future work. They provide, Adafruit does on the breakout board for the node, they give you a voltage divider hooked up to the battery, so I'm able to monitor the battery voltage. And that's actually currently the only data that I am logging, and I have a visualization of that that I'll show you at the end of the presentation of it actually logging the data in real time right now. In terms of future work for the firmware, definitely want to add a low power sleep mode, because if you're not going to be wanting to send data constantly, so you probably want to save as much power as possible while you're not sending. That's just common sense. And there's also an acknowledge transmission that happens after the node sends data that the gateway sends back, and the node will continue to send the same packet until it receives an ACK. So you could theoretically have a loss in time continuity if there was a signal dropout and the node tried to send the same packet over and over, and then when it would finally send that one, it would read new data, so you would lose data over the time that you were trying to send the same packet. It's a minor detail. So now on to the gateway firmware. So like I said, this processor that I've chosen allows for either wired USB serial or a wireless connection to the server. Wireless will be easier because it's wireless, and because it would allow for less code overall, because the way the backend is designed, I'll talk about that in a minute. There is data is input to the database with a GET request. It's just it's just URL encoded. It's nothing fancy. So the fact that there has to be an extra tool to do reading of serial converted to the GET request is just basically more complicated. But I didn't want to do the Wi-Fi, so this script was no problem. And the gateway could also be implemented as a repeater for longer ranges between nodes. And it again sends an ACK if the valid packet is received. I talked about that. So now, this gives you an overview of the server software. There's a lot of different languages mixed in here. There's a Python script that does the USB to serial to GET request conversion that I talked about. It actually says post here. It URL encodes the variables, so it's essentially the same thing. Flexible insertion by gateways connected over the internet. I've talked about that. So basically right now I have it set up to where when the computer starts up, it starts this Python script as a daemon in the background, and it just opens up the COM port, the device file that gets enumerated from the gateway over USB serial, and it just parses everything that the gateway sends it over serial and extracts the relevant data. And as soon as it gets that relevant data, it creates a GET request and sends that over a local socket to the web server that's running, and there's actually a PHP page that does the insertion into the database. If I wanted to use this Python script as the actual end result, I could totally just use a MySQL library in Python and do the insertion right there, but since I already had the PHP written, it was just easier to do that. And then the front end, you'll see that here in a little demo I show in a bit. That's written in Google Polymer, and it basically uses Google Charts to plot the data and automatically do axis scaling and stuff like that. So you'll see that here in a minute. The database that I created for it, pretty straightforward. It adds a timestamp automatically, 2 tables. I don't even use the params table right now. That just basically just allows, if there's more data context, it pretty much allows you to keep track of metadata that's associated with the data log data. So that's the database that the PHP inserts into, and the PHP is too much to put on a slide, so it's in the server folder under the app folder in the repository. So now I think it's time for a demo. Yeah.